In our previous videos, we have studied the fundamentals of DC machines. Let us now see what are the types of DC generators. Now you know that in DC machines, normally we use electromagnets because there are many advantages of electromagnets over permanent magnets. Now these electromagnets, they produce magnetic flux when current is circulated through the field winding. This circulation of current in the field winding, it is called as excitation. So in DC machines, excitation of field poles is essential to produce the magnetic flux. DC generators are mainly classified according to the way in which their fields are excited. Let us now see the classification of DC generators. So as seen earlier, DC generators are mainly classified according to the way in which their field is excited. So there are mainly two types of DC generators: separately excited DC generators and self-excited DC generators. Now in separately excited DC generators, field magnets are excited from an independent external source of DC current. Means in separately excited generator, separate independent DC supply is used to circulate the field current, and the other type is self-excited. In self-excited generators, field magnets are excited by the current produced by the generator itself. Means the EMF induced in generator itself is used to circulate the current in the field winding. So basically, according to the way of excitation, mainly there are two types: separately excited and self-excited. Now according to the way in which armature and field winding are connected to each other, these self-excited generators are further classified into three types. So these three types are DC shunt generators, DC series generators, and DC compound generators. Now in case of shunt wound generators, the field windings are connected in parallel with the armature. So if field winding and armature are connected in parallel to each other, then the generator is called as DC shunt generator. Now in case of series generator, field windings are connected in series with the armature. So if armature and field winding both are connected in series, then the generator is called as DC series generator. Now the compound generator is combination of shunt and series. So compound generator has both shunt and series field winding. So if both series and shunt field windings are used, it is called as compound generator. Now according to the way in which shunt and series field windings are connected, these compound generators are further classified into two types. These are called as short shunt compound generators and long shunt compound generator. Now we will see each type in detail. Let us now study separately excited DC generator. So you can see that in this case, field winding F1, F2. So this is the main field winding F1, F2, and it is excited by using separate independent DC power supply. And the voltage of DC power source is VF volts. Now here the current flowing through the field winding is IF and resistance of field winding is RF. Here R is the external resistance connected in series with the field winding. The function of this resistance R is to control the current IF which is flowing through the field winding. Now the generated EMF in armature is EG. Armature terminals are marked as A1, A2. Armature current is IA and resistance of armature is RA. Now if load is connected across the armature, load current will flow. Now here load current is IL. Now for this separately excited DC generator, we can write important expressions. So first of all, the current IF, it is given by supply voltage VF divided by total resistance, and here total resistance is R plus RF because both are connected in series, and therefore in case of separately excited DC generator, IF is equal to VF upon R plus RF. So here VF is the voltage of separate independent DC supply used to excite the field winding. R is the external resistance and RF is the resistance of field winding. Now load current IL and armature current IA are equal, and therefore IA is equal to IL. Now if you apply Kirchhoff's voltage law to this loop, then the generated voltage EG will be equal to terminal voltage V plus voltage drop in armature plus voltage drop across brushes. Now voltage drop in armature will be IA into RA, and therefore we can write EG, that is generated EMF in armature, is equal to V, that is terminal voltage, plus IARA plus V brush. So here IARA is voltage drop in armature and V brush is brush contact voltage drop. So this relation is important for separately excited DC generator. EG is equal to V plus IARA plus V brush and IA is equal to IL. Let us now study DC shunt generator. Now we have seen that in case of DC shunt generator, field winding and armature are connected in parallel. So here the field winding, that is F1, F2, it is connected in parallel to A1, A2, and full generated voltage is applied to the field winding. and this voltage circulates current in the field winding, which is denoted by ISH, and therefore this ISH provides necessary excitation to produce the magnetic flux. Now here the resistance of field winding is RSH and current through field winding is ISH. Again, generated EMF is EG. RA is the resistance of armature and IA is the current through armature. And again, load current is IL. Now for DC shunt generator, with the help of this diagram, we can write the important expressions. So first of all, the field current ISH. So voltage applied to the field winding is V and resistance of field winding is RSH, and therefore current through field winding ISH is equal to V upon RSH. So in case of DC shunt generator, ISH is equal to V upon RSH. Then if you apply Kirchhoff's current law at this junction, you can see that IA is the incoming current, whereas ISH and IL are outgoing currents, and therefore IA is equal to ISH plus IL. So armature current is the sum of field current and load current. Then again, by applying Kirchhoff's voltage law to this loop, Eg is the sum of terminal voltage V plus voltage drop in armature plus brush contact voltage drop, and therefore Eg is equal to V plus IARA plus V brush. So here IARA is voltage drop in armature and V brush is brush contact voltage drop. Another type of self-excited generator is DC series generator. So we know that in case of DC series generator, the field winding S1, S2, it is connected in series with the armature A1, A2, and thus armature current is circulated through the field winding, which gives necessary excitation and magnetic flux is produced. So here the resistance of series field winding is RSE and current through it is IA, or you can say IL, because all are connected in series. Then Eg is the generated EMF, resistance of armature is Ra and current through armature is Ia. And once again, if the generator is loaded, load current will flow and load current is IL. Now for DC generator, with the help of this diagram, we can write some important expressions. So first of all, from the diagram, you can see that IA is equal to the current flowing through series field winding, that is ISE, and it is also equal to IL. So here IA is equal to ISE is equal to IL, because armature, field winding and load all are connected in series. Then Again, by applying Kirchhoff's voltage law to this loop, we can write Eg as Eg is equal to terminal voltage V plus voltage drop in series field winding plus voltage drop in armature plus brush contact voltage drop. And therefore, Eg is equal to terminal voltage V plus IARA plus IARSE plus V brush. So here IARA is voltage drop in armature, IA into RSE is the voltage drop in series field winding, and V brush is the brush contact voltage drop. We have seen that there are two types of self-excited generators, DC shunt and DC series. Now we will see what is the difference between shunt and series field winding. So regarding connection, you know that in case of DC shunt generator, field winding is connected in parallel with armature, whereas in case of DC series generator, field winding is connected in series with armature. Now current in the field winding. So here in case of DC shunt generator, armature supplies the load current as well as the field winding current, and therefore the current through shunt field winding should be low, and therefore in case of DC shunt generator, ISH is small, whereas here as the field winding is connected directly in series with armature, armature current IA will flow through the series field winding, and therefore in this case the field current is large. So in case of shunt generator, field current is small and it is about 10% of the armature current, whereas in case of DC series generator, field current is large and it is equal to the armature current. Now resistance of field winding. Now if RSH is low, it will overload the generator. It will draw large current from armature, and therefore RSH must be large so that current ISH is limited. Whereas here series field winding is in series, and therefore if its resistance is large, it will produce large voltage drop, and therefore resistance of series field winding should be as low as possible, and therefore resistance of shunt field winding is large, whereas resistance of series field winding, it should be as low as possible. It is very small. Then number of turns. Now as shunt field winding current is small, we need large number of turns to produce the necessary ampere turns. And here as the current is large, few turns are sufficient, because ampere turns is the product of number of turns and current, and therefore in case of DC shunt generator, as the field current is small, there are large number of turns of thin copper wire, and here as the field current is large, we need few turns of thick copper wire in case of DC series generator. Then the most important is variation in field current. Now here if there is change in load, IL will change but ISH will remain almost constant, and therefore with change in load there will not be much change in field current in case of shunt generator. Whereas here, if the load changes, current in series field winding will also change, because armature current or load current is flowing through the series field winding, and therefore in DC shunt generator field current is almost constant from no load to full load, whereas in case of DC series generator field current varies with change in load. The third type of self-excited generator is DC compound generator. And according to the way in which series and shunt field windings are connected, there are two types of compound generators, short shunt type and long shunt type. Let us first see short shunt type compound generator. In short shunt type compound generator, the field winding, shunt field winding F1, F2 is connected only across the armature A1, A2, and the series field winding S1, S2, it is connected in series with this combination. So in this case, shunt is only across armature, and then this combination is connected in series with the series field winding. As the shunt is only across armature, the name is short shunt. Now in this case, the current in the series field winding is the load current IL. Now for short shunt type compound generator, with the help of this diagram, we can write important expressions. So first of all, applying Kirchhoff's current law here, IA is equal to ISH plus IL. Because IA is the incoming current, ISH and IL are the two outgoing currents. Now current ISH is equal to voltage across the shunt field winding divided by RSH. Now let this voltage is V dash. Now here V dash is V plus voltage drop in series field winding, and therefore V dash is equal to V plus IL into RSE. So next expression is ISH is equal to V dash upon RSH, where V dash is equal to V plus IL into RSE. Now by applying Kirchhoff's voltage law to this loop, we can write EG is equal to V plus IARA plus ILRSE plus V brush. So here IARA is equal to voltage drop in armature, ILRSE is equal to voltage drop in series field winding, and V brush is brush contact voltage drop. The second type of compound generator is long shunt type compound generator. Now in long shunt type compound generator, the field winding F1, F2, it is connected in parallel across the series combination of armature and series field winding. So here series field winding S1, S2 is first connected in series with armature, and the shunt field winding F1, F2 is connected across the series combination. So as the field winding is connected across both armature and series field, it is called as long shunt type compound generator. Now, with the help of this diagram, we can write expressions for long shunt type compound generator. Now, applying Kirchhoff's current law at this junction, we can write IA is equal to ISH plus IL. Then current through current through shunt field winding, it is voltage across shunt field winding divided by resistance of shunt field winding, and therefore ISH is equal to V upon RSH. V is the voltage across shunt field winding and RSH is the resistance of shunt field winding. Then by applying Kirchhoff's voltage law to this loop, we can write Eg is equal to V plus Ia into Ra plus Ia into Rc plus V brush. So here Ia-Ra is voltage drop in armature, Ia-Rc is voltage drop in series field winding, and V brush is brush contact voltage drop. Compound generators are also classified as cumulative and differential compound generators. In compound generators, normally the shunt field is stronger than the series field. Means the shunt field is dominating in compound generators. Now, if series field and shunt field both are in the same direction or both are additive to each other, then the generator is said to be cumulatively compounded generator. Means in cumulative compound generator, series and shunt fields are in the same direction. On the other hand, if series field opposes the shunt field, the generator is said to be differentially compounded. Means in differential compound generator, series field and shunt field are in opposite directions. So in this video, we have studied different types of generators. In our next video, we will solve few numerical problems on these different types of generators. Thank you. Stay home, stay safe.